Hello, everybody. Welcome to Appendix A, this little side section about proof writing basics. How do you write proofs? What is a proof? Why are proofs? How are proofs? Well, first, I'm just going to kind of talk about these paragraphs that I've written here. If you prefer to read them, you can skip ahead a little bit, but I'll just give it out in like a verbal sort of form. So, what is a proof? A mathematical proof is a written or spoken argument which should convince the reader beyond any doubt that a statement, sometimes called a proposition or a theorem, is true, as long as the reader has the background knowledge required to understand it. So, math is kind of special because we really mean this like any doubt thing. Other kinds of science, there's always a little bit of uncertainty. You're always using some kind of measurement devices where things might be off by a little bit. So that's always an issue in sciences, but in math, we're just talking about ideas where things mean what we've defined them to mean. And so proofs mean a lot more in math than they do in other fields. So yeah, writing and reading proofs is what mathematicians do all day. That's how you do mathematical research. In the same way that experiments are the same way that scientists do scientific research. Most mathematical papers and journals are, theorems and then their proofs. And then some discussion about what other theorems that might be true and how you might go about proving them and stuff like that. But proofs are the bread and butter of math. Now, when you write a proof for an assignment in math class, it serves a bunch of purposes. It shows me that you understand why the theorem is true, so I can grade it. But it also gets you to actually understand the theorem by studying the definitions and theorems and examples related to the thing you're proving, to actually understand the thing. And also, in a broader sense, we're not just here to learn linear algebra. We're here to practice reasoning and communication skills, which is what a big part of what college is about. So let's talk about the concept of a definition, because in math, definitions are different than they are in a dictionary. Dictionary descriptions are descriptive, which means that they describe the different ways people use a word. And if people are using a word and other people are understanding what they mean, there's no right or wrong there. People understand, so you said it right. Here's an example of that. If I go to google.com and I type in the word literally, I get this definition here. It gives me two versions of it. One is in a literal manner or sense, exactly, like the driver took it literally when asked to go straight across a traffic circle. Whoops, that means they actually drove straight across. Or people also use it in the opposite way as that. Like I was literally blown away by the response I got. Now, this part of the definition includes not literally. So literally both means literally and not literally. So this is a problem for people using the English language if you wanted to prove something beyond a reasonable doubt or beyond any doubt about the word literally, if something was literal or not. Because which version do you mean? Do you mean literally or not literally? So this is a problem for philosophers, for example. So when people ask questions like, what is the meaning of life? That depends on your definition of the word meaning and the and of and life, right? Questions like this are especially hard because different people mean different things by all these words. So that's one of the reasons I'm not a philosophy teacher. So in math, definitions can be prescriptive, which means that when we give you a definition, we're telling you what that word means right now, at least in the paper or the book or the course that you're in, with no room for nuance or interpretation. They should be clear and inarguable. So sometimes different people do use different definitions. Like, for example, some people say the set of all natural numbers starts with 0, and some people say the set of all natural numbers starts with 1, and they have fights about this. But it's not that big of a deal, because whenever you're reading a certain book or a certain paper, the person is going to define what they mean, whether 0 counts as a natural number or not. And then for the rest of that book or paper, everybody can agree. All right, so here's an example of a definition. An integer m is even if it can be written in the form m equals 2k for some integer k. An integer n is odd if it can be written in the form n equals 2k plus 1 for some integer k. So whenever, from this point on in this class anyways, whenever you see the term even integer, you know that that's a shorthand way of saying an integer that can be written as 2k for some integer k. And we're using a definition, we're using a term even instead of just writing this all out every time, because sometimes it would be really tedious and hard to understand to write out the whole long version of the definition. So, for example, if x and y are odd integers, then x plus y is an even integer. That's something you can read and understand and make sense. If we didn't have definitions for terms, we would just be writing everything out the long way like this. If x and y are integers that can be written x equals 2k plus 1 and y equals 2c plus 1 for some integers c and k, then x plus y equals 2p for some integer p. And that is also correct. It means exactly the same thing as 1. It's just that statement 1 is quicker and a little easier to understand in a hurry. And when you get more and more complicated things, the long versions of mathematical statements can get out of control really quickly. Now, when we use the word even from now on, just to reiterate, it means this definition. You can't say, like, 1 million is a nice and even number because it's nice and rounded, but this is not an even number, 998,576, because it is an even number. So, or you could say 0 is an odd number because it's the only number that can be added to other numbers without changing them. By that you mean the English word odd, which might be like it's a special number or an unusual number. So don't use the word odd for that. Okay, so those are mathematical definitions. Now let's talk about how to actually write proofs. What do you do when you have a problem that says to prove something and you don't know where to start? So here's a strategy. So step 1 is on scratch paper. Get some intuition for why the proof is true. Maybe come up with examples, maybe draw pictures of the examples. And that is one thing you can do to get an idea why it's true. You might also, as part of step 1, study the definitions and theorems related to this, talk to other people about it, get help, that kind of thing, until you have an idea why it's true. Then to actually start writing the proof, step 2, you're going to write assume P. So this statement is of the form if P, then Q. So you write assume P, but instead of writing just P, write it in expanded terms using the definition, like the long version of it. Then we're going to write want to show, WTS for short, want to show Q, but again with Q written in expanded terms using the definition. And 4 is draw the rest of the owl. Like actually do the proof. Use your assumption of P and any facts you know to show that Q must also be true when P is true. And also it's nice to end the proof with some kind of symbol, I draw a little happy face box. Some people write QED, which is Latin for something, and that lets the reader know that you are done with the proof. Now, steps 1 and 3 are optional because a proof can be perfectly valid and convincing without them. Like, if you just know how to do the proof, you don't need to do anything on scratch paper. That's fine. The want to show is sort of like a guide that you should use if you don't know how to write the proof. But lots of great mathematicians still write that at the top of their proofs because it gives you an idea of where you're going. Okay, so let's look at an example of how you might do these steps. So first of all, for step 1 on scratch paper, because you don't want to turn this stuff in, we're trying to get some intuition for why this is true, that if x and y are odd integers, then x plus y is an even integer. So, Now, by the way, you might have a perfectly good idea why this is true. Maybe you don't need to do this at all, but it's good to think of some examples of odd integers. So let's see. X could be 3, and y could be 7, and that makes x plus y equal to 10, and that is even, right? Let's just make sure this is odd using the definition. 3 is 2 times 1 plus 1. 7 is 2 times 3 plus 1, so that's what it means for those to be odd. And 10 is 2 times 5, so that works. Okay. Maybe, what if we wrote x plus y in this expanded term? Maybe that will help us see why this works. So that's x, y is 2 times 3 plus 1. And maybe you could like combine some like terms, like these are all multiples of 2 in front, so you could write that as 2 times 4. And then the 1 and the 1 combine to make 2. And you can write that as 2 times 4 plus 1. Yeah, 2 times 5. Okay. And at this point, you might see how it works. You might need some other examples. You might try a negative odd number just to see if it's different with negative odd numbers, but maybe you get the idea at this point. So let's go on to step 2. So we're going to start actually writing the proof. So we are going to assume that x and y are odd integers, and based on that assumption, try to show that x plus y must be even. So, but instead of writing just assume x and y are odd integers, we're going to use the expanded version in the definition. Okay, so that is step 2. That's what we know is true, and we want to show that based on that, the conclusion that x plus y is even must be true. And writing that out is step 3. But we're not just going to say want to show x plus y is even. To make it clear that we're using this definition, we want to show that x plus y is equal to 2p for some integer p. And by the way, I'm using k and c and p here. It really doesn't matter. You can use anything you want as long as it's not a letter that's already used for something else in your proof. So that's what we want to do. Now, step 4, draw the rest of the owl. Okay, so we want to show something about x plus y, and we have this thing we know about x and y, so let's write it in that form. X plus y is 2k plus 1, that's the x part, and y is 2c plus 1 for some integers c and k. Now, you can still use everything you know about math from your other classes. Like, for example, you know the distributive rule. You know that 2k plus 2c can be written as 2 times the quantity k plus c. And you know from other classes that 1 plus 1 is 2. Good. And can we write this? Can we get to this goal? Writing x plus y as 2 times something? Sure, we can still factor out another 2. And that is an odd integer, an odd number, because we have, this is the p, k plus c plus 1. Did I say odd? This is an even integer because it's written as 2 times an integer where the p is k plus c plus 1. And now anybody reading this who knows the definition and knows some basic math facts like the distributive rule is going to believe beyond any doubt that x plus y must be even if we started with odd numbers, x and y. All right, let's look at a definition. An integer n is divisible by an integer p if n equals p times q for some integer q. So just a quick example of that. Like 40 is divisible by 8 since 40 equals 8 times 5. Okay, so let's show that if n is an odd integer, then n squared minus 1 is divisible by 8. And this one is not nearly as obvious as the last one. So we're going to have to do a little bit of thinking about this. So you want to think of some examples of some odd integers, see what happens when you square them and subtract 1, and see why is that divisible by 8. So let's try, I don't know, n equals 7 sounds good. So if you do 7 squared minus 1, that's 49 minus 1 is 48. Yeah, okay, that's 8 times 6. That is divisible by 8. Interesting. Well, it helps to think of it using the definition. Like the definition is that 7 is some 2k plus 1. And, so when we do 7 squared plus minus 1, you can think of this as 2k plus 1 quantity squared and then minus 1. And we can FOIL that out. You'll get 4k squared plus 4k plus 1 minus 1. Oh, we're getting somewhere. This plus 1 minus 1 cancels out. And we can write this as like 4 times k squared times k plus 1. Like when we're showing something's divisible by 8, it helps to factor it as much as possible. So let's go ahead and take out the greatest common factor, the k. So we still have k plus 1 left over. Oh, okay. So yeah, we know it's divisible by 4, but then we have this other stuff. But I guess I should have said the k here is like 3. I don't know why I said k that whole time when it's a specific number. Okay, now at this point, 3 is odd, but 3 plus 1 is even. So yeah, this is the same thing as 4 times 3 times 2 times 2 here. And that gives you another factor of 2, which is, okay, there we go. We're getting somewhere. Let's see what happens if I do this with another number. Let's try n equals 13, which is 2 times 12 plus 1. If you do that squared, you're going to get 168, which is 8 times 22, I think. 21? 21. Yeah, so that is divisible by 8. Okay, What if we write this as using the definition? Oh, why did I say 2 times 12 plus 1? That was 2 times 6 plus 1. Okay, so 2 times 6 plus 1, quantity squared, minus 1. That's our n squared minus 1 here. FOIL this all out. We'll get 4 times 6 squared plus 4 times 6 plus 1, and then the original minus 1 out here, and those will cancel out. And then, oh yeah, we can see we can factor out a 4, and then we have a factor of 6 between these, and then another 6 plus 1 after you factor that out. And now I can see that 6 is an even number, which means that has a factor of 2. So that gives us a factor of 8. So now I'm getting the idea, and we can start the proof. Let's write steps 2 and 3 here. Okay, so that's our goal, is to show that n squared minus 1 is equal to 8q for some integer q, because that's what it means to be divisible by 8. Okay, let's see. So the n squared minus 1 we can write as 2k plus 1 quantity squared minus 1, just like we were doing before. FOIL that all out. Those terms cancel out. We have a factor of 4, a factor of k, and a k plus 1 left over. And here's the trick, which is that a thing you know about even and odd numbers, even though we haven't formally proven it, but you know that every number is either even or odd. And if k is even, then k plus 1 must be odd. And if k is odd, then k plus 1 must be even. So one or the other of them is odd, and one is even. So that gives you the other factor of 2 that you need. And so if k is even using the definition, we can factor that out, and that gives you 8 times that x times 2x plus 1, and that is divisible by 8. Likewise, if k plus 1 is even, then n squared minus 1, or we can just leave this as k, which is also divisible by 8. Cool. So that is the proof. That was a tricky one. I think the hardest problems in the homework are probably about as tricky as that, but most of them are kind of like the last one, where simple things about odd and even integers. All right, let's take a break and we'll come back in the next video.